In this experiment, you would determine if a reaction is exothermic, that is, one which gives off energy, or endothermic, one which absorbs energy. Your sense of touch is very useful in determining the heat flow as a reaction occurs, since exothermic reactions feel warm and endothermic reactions feel cool. This flow of energy can be represented in an energy diagram, a qualitative drawing showing the relative energies of the reactants and products. Recording the appropriate data before and after a reaction occurs allows the numerical value Q to be calculated for the reaction, which can then be converted into delta H, or enthalpy, for the reaction. You will record several masses in this experiment and use a calorimeter to measure the change in temperature for several reactions. An exothermic reaction gives off heat. This indicates that the reactants lose energy as the products are formed. To illustrate this difference using an energy diagram, a line representing the reactants is drawn at a higher level on the enthalpy axis, and a line for the products is drawn at a lower level. This drawing represents the qualitative difference in energy between reactants and products, and the x-axis may be considered in a general sense as the progress of the reaction. The difference between these two levels is, conceptually, the enthalpy change for the reaction. An endothermic reaction absorbs heat, products gain energy as the reaction progresses, and the products are drawn at a higher energy level on the enthalpy axis. The sign of delta H, which represents the enthalpy change during a reaction, for an exothermic reaction is negative. For an endothermic reaction, the sign is positive. When writing balanced equations, it can be useful to write the word heat as a product for exothermic reactions and as a reactant for endothermic reactions. A calorimeter is used to measure temperature changes of known masses of reactants during a chemical reaction. Ideally, it includes an insulated container that prevents any heat gain or loss to the surroundings during the progress of the reaction. A value for Q can be calculated if the masses of reactants and reactant solution are known and the temperature change is recorded during the reaction. The calculated value of Q represents the heat flow between the reaction and the calorimeter, where the calorimeter is defined as the physical container, the thermometer probe, and the solution in which the reaction occurs. For an exothermic reaction, as products are formed from reactants, the heat given off is absorbed by the solution containing the reaction. It is prevented from escaping by the insulating container, and the temperature change is recorded using a thermometer. The factors affecting the magnitude of Q are the mass and identity of the reactants involved in the reaction, the mass of the reaction solution in the calorimeter, and the temperature change during the reaction. The numerical value of Q is determined from the mass of the reaction solution, the specific heat capacity of the reaction solution, which is assumed to be 4.18 joule per gram Kelvin, and the change in temperature of the reaction solution. To ensure that the sign is correct on Q, don't forget to include the minus sign before the bracket, and also to subtract the initial temperature from the final one. The value of Q is based on the mass of the limiting reagent consumed in the reaction. Q is then converted into delta H, which is the heat change per mole of limiting reagent. The qualitative reactions in this experiment simply involve determining if the reaction is exo or endothermic and drawing the accompanying energy diagram. The quantitative reactions also require that Q and delta H be calculated for these reactions. Quantitative calculations require that the exact mass of the limiting reagent be determined. For both liquid 18 molar sulfuric acid and solid potassium thiocyanate, the mass of either can be directly converted to moles using the molar mass of the appropriate compound. For the acetic acid solution, its mass in grams can be converted into volume in milliliter using a density of 1 gram per mil. This volume can then be converted into mole using the acetic acid concentration, which is in molarity. Standard safety procedures include wearing safety goggles, lab coat, and closed-toe shoes. Gloves are also required for this experiment. Any skin exposure to an acid or base should be immediately rinsed with copious amounts of cold water. Notify your TA of any chemical spills on your bench or in your hood. Your TA will dispense the 18 molar sulfuric acid. The KSCN is a very sticky solid and is never weighed directly on a balance. Initially add an approximate amount of KSCN to your calorimeter at the reagent bench, then determine its mass on the balance. This is very messy solid to work with, and you should never transfer KSCN from the reagent bottle into a weigh boat that's positioned on a balance pan. KSCN will spill on the balance pan and it will corrode. Rinse your calorimeter with cold water and dry it with a towel between each reaction and when you are finished at the end of the lab period.